Welcome back. So let's now see how we can write force and moment units, which are Newton and Newton meter, in terms of meters, seconds, and kilograms. Let's start with force. We know that force equals the time derivative of linear momentum with respect to time. And from calculus, using the product rule, when you take the derivatives, you can write force out like this: dm over dt times v plus m times dv over dt. There is a more compact way to express time derivatives. Instead of dm over dt, you can simply write m dot. It's the same thing. And then dv over dt, well, that's simply your v dot. Let's take a look at the first term, m dot times v. M dot is the change of mass with respect to time. So its unit is kilograms per second. And then v is velocity. Its unit is meters per second. And so when you have m dot times v, that means that you have kilograms over second times meters over second, or simply kilograms times meters over second squared. Let's now check the second term, m times v dot. M is your mass, so its unit is kilograms, and then v dot, that's the change of velocity with respect to time. So that's meters over second, or simply meters over second squared. So v dot, that's your acceleration, and the unit of acceleration is meters over second squared. And so the total unit of the second term, m times v dot, that's kilograms times meters over second squared. You can see that it's the same that you had for the first term. And that's very good, because when you add two terms together, then they have to have the same units. Otherwise, it doesn't make sense. You cannot write meters over second plus meters over second squared. That's like trying to add apples and oranges together. It doesn't have any meaning. In our case, however, both terms have kilograms times meters over second squared, and that means that their sum, the force, its unit is also kilograms times meters over second squared, which means that the Newton can be expressed in terms of these fundamental units like this: kilograms times meter over second squared. And now when we talk about moments, since their unit is Newton meters, then it can be rewritten like this: kilogram times meters over second squared times m. So this part here, that's this part here, and then this part here, that's this one here. In other words, you can rewrite it like this: kilograms times meter squared over s squared. So that's how you express force and moment units in terms of these fundamental SI units. Now, in high school, you probably learned that F equals m times a. A is acceleration, or v dot in our case. It's the same thing. That's a special case. When you look at our original force equation, where you had two terms, one is here and the other one is here, then if you assume that the mass of the object which that force is applied to is constant, then that means that dm over dt, or simply m dot, it equals 0 kilograms over second. It's a mathematical way of saying that the mass is constant. It doesn't change. When that's the case, then this term here it will be 0 newtons. And then you're left with F equals m times v dot, or F equals m times a. So that's the special case where the mass of the object doesn't change. It's constant. It stays the same. That's the case for many problems in mechanics. However, for example, when you have a rocket that goes up, then it burns up fuel very fast, and then the rocket's mass is not constant, and this special condition doesn't hold. Then F equals in this original equation. Keep in mind that these equations are valid in the inertial frame. It means that if I have a reference frame here, x, y, and z, then all these velocity and acceleration measurements, they are with respect to this xyz reference frame. And the condition is that this reference frame itself, it doesn't accelerate tangentially, nor it rotates. It's an inertial frame. An inertial frame is a non-accelerating frame. And since when an object rotates, then it's also acceleration, because the direction of your velocity vector changes, that means that this inertial reference frame, it doesn't rotate either. It doesn't accelerate tangentially, meaning that the origin is not accelerating somewhere along some kind of line, and this reference frame is not rotating either. And so this law, F equals dmv over dt, it's called Newton's second law, and it assumes exactly that, an inertial reference frame. Or I've seen that it's also called an Earth reference frame. In many engineering problems, you take this reference frame and you fix it somewhere to the ground, and that's why it's also called an Earth reference frame. Finally, if we look at the force units in terms of the fundamental units, kilograms times meters over seconds squared, then it really gives us good intuition about what force really is. The force unit Newton, it consists of kilograms, which is the unit for mass, and meters over seconds squared, which is the unit for acceleration. So if you just imagine a box that floats in space, there is no force of gravity there, no force of friction. It simply floats somewhere far, far away from here in space. The mass of the box is 1 kilogram, and it's constant, it doesn't change. And so, how much force, let's call it FA, applied force, how much of that applied force do I have to apply to this box so that the box would accelerate 1 meter per second squared? Pause the video and give it a thought for 10 seconds. What would be the required applied force in order to achieve a 1 meter per second squared acceleration for the box whose mass is 1 kilogram? Well, the units of Newton are kilograms times meter over second squared. You have 1 kilogram, you need 1 meter per second squared, so your force is 1 kilogram times 1 meter per second squared, which is 1 kilogram times meter over second squared, or 1 Newton. And you can also get it from the force formula. F equals, and then m times v dot. So here m is 1 kilogram, and then v dot, that's 1 meter per second squared, and you get your 1 Newton force. What about if the mass of the box is 3 kilograms, and you want this box to accelerate 4 meters per second squared? Pause the video for 10 seconds and give it a thought. Well, F equals m times v dot, so 3 times 4, that's 12 newtons, or 12 kilograms times meter over second squared. So from here you can see that you can think of force in this way. If you have a 3 kilogram box and you want to accelerate this box by 4 meters per second squared, then you have to apply a 12 Newton force to it. So force, it's just another quantity from physics that ties up together an object's mass and its acceleration. And of course, if the mass is not constant, then your force formula is like this, and you can see that the quantity force, it ties up together the change of mass with respect to time, which is in kilograms over second, the velocity of the object, which is meters over second, the mass of the object, which is kilogram, and the acceleration of the object, which is meters over second squared. And of course, the units here and here, they are actually the same. And so in the most general way, you can say that force is a quantity that physicists use in physics that tells them how the linear momentum of an object changes with respect to time. It's simply another quantity that you can measure about an object. You can measure an object's mass, length. You can also measure how long it exists for, so time. And you can also measure force and moment, which is another quantity from physics. So that's what I wanted to say about that. Thank you very much. Welcome back. So let's talk a bit more about forces. Let's review the Newton's 3 laws of motion. The first law states that if you have some kind of particle that is at rest or that moves somewhere at a constant velocity, then it continues to be at rest or move at a constant velocity for as long as the forces acting on that particle balance each other out. In other words, your net force, which is F1 plus F2 plus F3, it needs to equal 0 newtons. And of course, there must be balance in all x, y, and z dimensions. So these force vectors, they actually look like this. So it's a 3 by 1 vector. And so the net force, it has to be like this, a 0 vector. Then the particle will remain at rest if it was at rest in the first place, or if it had some kind of velocity, then this velocity won't change. And then the second law states that when there is an unbalanced force applied to the particle, you can see that in this case, the force that goes down is very small compared to the two forces that point up. Because of that, you will have some kind of net force in this direction. Horizontally, the forces cancel each other out, but vertically, they do not. And so when you have this unbalanced force, F net, then assuming that the mass is constant, this particle will accelerate in the direction of this F net force. So the particle will accelerate in that direction. And in that case, F net equals the mass of the particle times the acceleration of the particle. But of course, if the mass of the particle is not constant, then F net equals the change of mass of the particle with respect to time times the velocity of the particle plus the mass of the particle times the acceleration of the particle. So in here, we assume that dm over dt equals 0 kilograms per second, and here we assume that it's not 0 kilograms per second. So in this general case, this net force, or the resultant force, you can also call it F resultant, or Fr, in this general case, it depends on 4 quantities, m dot, v, m, and v dot. And then the third law states that if you have two particles, let's call it particle A and particle B, if particle A applies some kind of force on particle B, so let's call it like this, F and then A arrow and B, so particle A applies force to particle B, then that means that particle B applies force to particle A, so FB arrow A, and this force here is equal in magnitude to this force here and opposite in direction. So if I have a wall here and I stand here and then I push this wall in this direction, then according to this law, this wall is pushing me in this direction with the force that has the same magnitude but it's opposite in direction. You will see that this law becomes very useful in statics and dynamics later on. And finally, after formulating the 3 laws of motion, Newton also formulated the law of gravitational attraction. It states that if you have two particles and their masses are m1 and m2, then there is gravitational attraction between those two particles. There is a gravitational force between them. And so this force of gravity, it's expressed like this: G times m1 times m2 over r squared. So Fg is the force of gravity between two particles. Then this G, that's a universal constant of gravitation. And from experiments, it was found to be 66.73 times 10 to the power of minus 12 meter cubed over kilograms times second squared. And then again, m1 and m2, they are the masses of these two particles. And then this r, that's the distance between the center of gravities of these two particles. And if we assume that this mass is distributed equally in the particle, meaning that you have a particle and then the density inside the particle is equal, then the center of gravity, it will be in the center of the particle. If you had a particle where, for example, here you have a lot more density and then here you have a lot less density, then your center of gravity would be maybe somewhere here. But we are not assuming that. We are assuming constant density, and so we can say that this r is the distance between the centers of these two particles. And now, let's assume that this is our planet, this is the Earth, and you have many particles inside your Earth, and let's say that you sum all the masses of these particles up, and now you have the mass of the Earth. Let's call it m sub e. And then we have another object here. It also has many particles here, and we also sum their masses up, and so let's call it mass A. That's the mass of this object. Here we will again assume constant density, so mass is distributed equally inside the Earth and inside this object. If we make that assumption, then the center of gravity of the Earth, it will be in the center of the Earth, and the center of gravity of this object A, it will be in the center of that object. And then we can say that the distance between these two centers of gravity is r, and so that means that the force of gravity between the Earth and this object A, it's Fg equals the universal constant of gravitation times the mass of the Earth times the mass of the object A divided by this r squared, which is the distance between the centers of these two objects, thanks to our constant density assumption. However, from the Newton's second law, you know that if the masses of those two objects are constant, meaning that they don't change, then force equals the mass of an object times the acceleration of that object. So now I have an exercise for you. Try doing it yourself before watching the next video. So there will be 3 questions. Knowing this formula for the force of gravity between these two objects, between the Earth and object A, the first question is, what's the acceleration of object A towards the Earth? And you have to express it in terms of these variables here. So express it in g, me, ma, and r. Then the second question is, what's the acceleration of the Earth towards object A? And again, express it in g, the mass of the Earth, the mass of the object A, and r. And then the third question is, does the Earth exert a stronger gravity force on object A or vice versa? So try it out and let's continue in the next video. Thank you very much.